Hello, class. Welcome back. We are continuing from the last lesson or last video, and in particular, what we want to talk about are properties of probability functions. And specifically, I mean the probability mass functions or probability density functions. This one is for discrete random variables, and this one continuous random variables. But I'm going to begin with an example that we talked about in the last lesson. We are rolling a fair six-sided die, which means every face has equal chance of landing up. And we have a random variable x1, which is the number of dots on the face turning up. Well, everything's equally likely. Now, one way we can display this probability mass function is with this table, where the function value is 1/6, well, for every possible outcome. Now, we had these events last time, A, B, C, and D, and we calculated the probabilities by taking the cardinality in A, or a number of outcomes in A, divided by the cardinality of S, or the total number of outcomes. And this is perfectly fine. However, if we write this in the language of this random variable, let's see, if we want the probability that x1, the random variable, is in the set A, well, it's 1/6. Let's do this one, the probability that x1 is in the set C. Here, I'm going to introduce this notation, which we'll build on in the next example. What we just do is we add over all little x and C of f of x. And in this case, you notice this is 1/6 plus 1/6, which is 1/3, as we calculated before. And similarly, we could write probability, the random variable lies in the set B, and we add over little x in B, f of x, and here, well, it would be 1/6 plus 1/6 plus 1/6. And finally, just getting used to this notation, the probability that this random variable lies in the set D, this was the sum, little x is in D of f of x. And there's 5 things here, so it's 5/6. We already calculated these before. I'm just illustrating this new way of thinking about it. Now, as a remark, and this is quite important because we're about to get into some properties very shortly. If you take the entire set S, 1, 2, 3, 4, 5, 6, the probability that the random variable lies in S, well, if you don't know, just add up all of the elements in S. In fact, I'll write this. Let's add up over all of the x in S. But you notice we're adding up 1/6 6 times. This is 1. Now, of course, this makes sense. This is just saying what's the probability that you get one of the faces, 1 through 6, when you throw a die and you look at what's landing face up. Well, this happens with probability 1, of course. Next example. Well, now I have a new die. It's still six-sided, but it's unfair. Outcomes 1 through 4 and 6 are all equally likely. However, outcome 5 is 5 times more likely than each of the others. So we have a new random variable x2, which is the number of the dots on the face turning up when we throw this unfair die. Well, we can figure out the probability mass function here. So first, let's say that f of 1, which is the same as f of 2, f of 3, f of 4, and f of 6 or all some value. I don't know what it is. I'm just going to call it P. And then some probability, right? P. And then we know that f of 5 is 5 times this much. Well, how can we figure out what this is? Okay, we can use kind of the idea in this remark that you know one of the 6 faces will turn up. Probability 1. We must have probability of 1, probability of 2, probability of 3, probability of 4, probability of 5, probability of 6, all of this to equal 1. So what do I have here? I have a total of 10p equals 1, and this p is 1 divided by 10. Well, now I'm ready to fill in my chart. So we have 1 over 10 in all of these except for 5, in which case we have 5 over 10, or 1/2. All right, well, we can do exactly the way I worked it the second time, which is add up. So here, this first one is the simplest to calculate. In fact, we've already done this. The probability that x2 is in A is 1 over 10. We just evaluate at 2, which is right here. Now, for B, the probability x2 is in B, you see we have to add, maybe I will write this, overall little x in B, f of x. Okay, well, we know 1, 3, 5. So we take 1 over 10 plus 1 over 10 plus 1/2. Altogether, I have, let's see, 5/10 and 2/10 makes 7/10. So we have 7 over 10. Here's this answer and this answer. The probability of that x2 is in C, this would be a sum over all little x in C of this new probability mass function. And well, we're adding 5 and 6, so we have 1/2 plus 1/10. 5/10 and 1/10 is 6/10, or 3 over 5. Finally, the probability x2 is in D, well, it's a sum over little x in D of this new probability mass function evaluated at that x. Now, let's look at it. I won't write out the sum because I'm running low on space, but we have 1, 2, 3, 5, and 6. So what is the sum? Well, there's 4/10 plus 1/2. Maybe I can write that part. 4 over 10 plus 1 over 2. We get 9 over 10. Now, if you go back, you'll notice these are not the same as the probabilities when you have a fair die. Now, I want to move into properties of the probability mass functions, probability density functions. But first, let me give a definition because it's just language that's going to come up now and throughout the course. So if we have a random variable, this is usually what I will say is the support. You might also see this as the range or the sample space of this random variable x. Well, it's just the set of possible values of the random variable. So for example, in both x2, this random variable with an unfair die, and x1, where we had a fair die, the support is the integers 1 through 6. Okay. Well, now let's talk about some properties. And just as we did before, I like to put discrete and continuous side by side. The first thing that I really want you to understand in these properties is not every function can be a probability density function or a probability mass function. We have requirements, and that's what I'm going to talk about first. So suppose over here in the discrete world, here S is, well, well, you can think finite or countably infinite. We discussed this in the last lesson. This would be, for instance, positive integers or all integers, something like this. Or s can be finite. Well, then some function f, which is defined on this set S, is a probability mass function. This is my abbreviation for some random variable x, provided, well, we need two things. Property 1, well, the function needs to be greater than or equal to 0 for all x in this set S. That's property 1. And the second one is if you sum over all x in S, f of x, you get 1. Any function on a finite or countably infinite set that satisfies both 1 and 2 will be a probability mass function for some random variable. Now, in the continuous world, we know that we are not summing here, but we can say something similar. In this world, let's say our S is an interval, typically, and then any function defined on S is a probability density function for some random variable, provided, well, it's almost the same, but we know the world of the continuous random variables and the world of the discrete random variables are different. So the first thing actually looks the same. We need the function to be non-negative for all x and x. But the second one, this is where things change. So in the discrete world, we add to calculate probabilities. The continuous world, we integrate. So what we need is you integrate over all x and s, f of x, dx, and we get 1. So these are the two properties that we need, both for a probability mass function or probability density function. I just made this slightly smaller because I want to make a remark. This we actually saw in the last example, and then I'll also make a remark about the corresponding statement in the continuous world. So in this world, if you want the probability that your random variable lies in a set A, you just sum, just as we saw, little x in capital A of f of x. This is in the discrete world. Whether you're working with a finite set or countably infinite set. Now, the corresponding probability calculation in the continuous world, and we started discussing this in the last lesson, we are not summing here. In the continuous world, probabilities are areas. And so we would integrate overall x and A of f of x dx. All right, here are 3 examples from lesson 1 that we just used, but we will verify using property 1 and property 2 that we have, well, either a probability mass function, the only discrete one is here, or a probability density function. In the last lesson, we just kind of took my word for it and worked with them. So let's see, I have the graph of this bottom one. Now let's verify. So property 1, well, we need f of x to be greater than or equal to 0. Well, the function is just 1/5. Certainly that's greater than or equal to 0. Okay, very nice. Property 2, really, this is a statement about an integral. So we need the integral from 130 to 135 of 1/5 dx. just as I did in the last one, we can just think area. Well, the area here you see, it's a rectangle where the base is 5, the height is 1/5, and so we get 1. So this is a check mark. Very nice. So we have verified. Now, the next one, this is discrete. So, okay, property 1 is still about the function being non-negative, and that is true. So x over 8 is definitely, in fact, it's strictly positive for x equals 1, 3, and 4. Not a problem. Now, property 2, this is a discrete random variable, and so we need to evaluate a sum. Well, we should have 1 over 8 plus 3 over 8 plus 4 over 8. This should equal 1. In fact, it does. We have 8 over 8, which is 1. Very nice. Last one, let me shade the area under the curve. Well, we can see by looking at the graph, property 1 holds because I have a graph. So property 1, y over 8 is greater than or equal to 0 on this closed interval, 0 to 4. In fact, we see it in the graph. Now the second one, property 2, this is a definite integral. In fact, I'll write it that way. What we want is the integral from 0 to 4 of y over 8 dy. Well, I'm just going to do area here. So the base is 4. The height is 1/2. And then we have 1/2 base times height. And so we get 1. In fact, I actually used this in part of my calculation in the last video. Okay, great. So we have finished these 3 problems. Okay, we have one more page of examples here, but it's a question. Is this a probability mass function? Is this a probability mass function? Is this a probability density function? You notice the formula is the same in all 3 of these. Okay, well, if the answer is yes, I have 2 things to verify. If the answer is no, I just need to justify that one of the 2 things fails. Immediately, I know this first one is a no. Why is that? Well, you notice that f of 0 is 1 over 18 times 0 minus 1. This is negative 1 divided by 18. We will not see a negative value for a probability mass function. Okay, no. Now, next one. Well, here, f of 2 is 1 over 18 times 4 minus 1. I will simplify that in a moment, but already we can tell this is positive. F of 4 is 1 over 18 times 16 minus 1. And once again, we can see 16 is bigger than 1, so this is positive. So property 1 is great. Property 2, I just need to add f of 2 and f of 4 and see if I get 1. Okay, let's do it. Property 2. F of 2 plus f of 4. Well, here's where I will simplify these. F of 2, you see, is 3 over 18. And f of 4 is 15 over 18. Oh, we get 18 over 18, which is 1. So this also holds. So the answer here is yes. Let me answer my own question. Okay, last example. Here we have this interval of values. So I'm checking to see if this is a probability density function. Well, 2 squared, 4 squared, and really anything between 2 and 4 squared minus 1 will be positive. And so we can see looking at it that the function is greater than or equal to 0, in fact, strictly positive, but I'll stay it this way on this interval 2 to 4. So far, it looks okay. But now the question, what is this? The integral from 2 to 4 of 1 over 18 x squared minus 1 dx. Now, do we want to integrate this? Unlike the examples we've seen so far, it's not a geometric object where I can just use a formula, say area of a rectangle or area of a triangle to figure out the area. Now, in this case, it's just a polynomial. And so we could certainly use the fundamental theorem of calculus, find an antiderivative, evaluate at 4, evaluate at 2, and take the difference. But throughout the semester, I'm not expecting you to remember any of the rules of integration. In fact, some things won't be so simple to integrate. So we can answer this question using R. Here's my function defined, function 3 in this third example, and I can just ask R to integrate this function. The lower limit is 2, and the upper limit is 4. And you notice I do not get 1. Let's go back and we will write that this is approximately, what does R tell us? Let's see, 0.9259. That's okay. But the answer is no. Now, at this point, we are not done with this lesson. We are done with the lecture part, the lecture video. So you should click through Canvas and practice some of the more commands in R working with probability mass function and probability density function. Thank you so much.